So we have learned many things so far to prepare. That's the preparation for the study of the combinatorics of orthogonal polynomials. So this is basically the first part of our study. So we will first review the definitions and fundamental results in orthogonal polynomials that we learned already. And then we will talk about how we can study them combinatorially. So this section will be a lot of repetitions, but our focus is now on formal orthogonal polynomials. So instead of before we considered orthogonal polynomials on with real coefficients or complex coefficients, but now it will be just any coefficient can be anything, just any ring element. So from now on, let's say K is a field. Any field can be fine, or we can even consider a ring, commutative ring. If division is not used, if we build our theory without division, then we can also work with a commutative ring. But just for simplicity, I'm gonna just say that F is a field. K is a field. So just notate the review of the notation. So this is the ring of polynomials with in X, polynomials in X with coefficients in the field K. All right, and we also defined a linear functional. Linear functional is just a linear map, which we denote from this ring of polynomials to how can I say? Yeah, to the ring. Yeah, anything. So by linear is you can think of this as a vector space. A field is a vector space. This is also, we can give a vector space structure, so it satisfies the vector space structure. So that means i.e. L of A fx G B Gx equals A L of fx B L of Gx. Yeah, we already learned this. This is just a review. So, and the nth moment of L is, we denote this by mu sub n. This is L of x to the n. So nth moment can be defined in this way. And now we can define a sequence of orthogonal polynomials. So a linear functional, and a sequence of polynomials P sub n is an OPS, orthogonal polynomial sequence, for L if the following holds. So first, do you remember this? Pn has degree n for every n. And second, the orthogonality, Pmx, Pnx must be 0 for all m and n different. And third, this is non-zero. And also, we also say sometimes we'll just don't talk about the linear functional, and then we can also say that this is an OPS for the moment sequence, and also like, and we can also say that this is the moment, nth moment of the OPS. Sometimes we will say like this. So, and like I said, K is not necessarily the field of real numbers, so it can be anything. It can be like, so we may have many parameters in our field K, like A, B, C, D, etc. So K, we can even have rational functions in our field K, and also like formal power series or anything like that. So we have a lot of flexible here. So as long as we have these three conditions, and we say that it's an orthogonal polynomial sequence. So sometimes people say it's a formal orthogonal polynomial, or some people say like general orthogonal polynomials. So K can be anything, any field. So sometimes such OPS is called like a general OPS or formal OPS. All right. Okay, so let me give you another review on this proposition. So suppose that P and X is OPS for a linear functional L. Okay. Then we have the following. Then P and X is OPS for L prime, which is defined to be A times L, A different from 0. So it's another linear functional, which is just the same linear functional multiplied by a constant, and it's also the original orthogonal polynomial is also OPS for this new linear functional, and L is uniquely determined up to scalar multiplication. That means this is OPS for only one linear function up to scalar multiplication. That's what this means. In other words, if this is OPS for L and also OPS for L prime, then L and L prime must satisfy a relation like this for a constant. That's and 3. If this is actually the same, so let me write it this way. And also, Pn is also determined uniquely in this sense. Is OPS for L for any constant a and non-zero. Okay. So we already proved this before, so I'm not gonna do this again. But because of this, we can always make the coefficient, the leading term, anything that we want. So, and because of this, we can make this to be any non-zero number. So we will assume from now on, because of this, we always assume the following. Degree of Pn is always n. This is always assumed unless I say otherwise. And also, linear functional applied to 1 will always be assumed to be 1, because otherwise we can multiply this so that we can make it. And also, P and X is monic. We will only consider monic OPS because we can do that. Yeah, and that's the most natural in the combinatorial study of orthogonal polynomials. Okay, so these three will always be assumed. Okay, and also we have learned important theorem like this, three-term recurrence. So P n is OPS for a linear functional L. Then there is a sequence, two sequences, Bn indexed from n from 0 and lambda n from 1, such that these orthogonal polynomials satisfy this three-term recurrence, Bnx. Because it's monic, we can write this way. For all n greater than or equal to, say, 0, where initial condition, of course, is 0, is 1. Actually, I have to mention that we have to have this condition, lambda n must be non-zero. Lambda n must be non-zero. Bn could be 0, but lambda n is non-zero. Okay, so three-term orthogonal polynomials always satisfy a three-term recurrence like this. This is things that we learned, and the inverse of this also true, which we called Favar's theorem. So if Pnx and good satisfies, let's say this condition star, the recurrence star, then it is OPS for some linear functional L. So in other words, it is an OPS. Yeah. So yeah, we have a So what do we want to do in this chapter? So our goal here is find combinatorial models. For polynomials themselves and moments. So we have two things that we want to do. We want to give some combinatorial meaning to polynomials, and we also want to give some combinatorial meaning to the moments. Yeah, and in fact, it's quite simple to find a combinatorial model for this because we have a nice, simple and nice recurrence. We can just make a combinatorial meaning to it using this recurrence, and that's what we will do. But this is more interesting. Yeah, we will see that. And using this combinatorial models, we will prove Favar's theorem combinatorially. Yeah, we can do that. That's and maybe prove Favar's theorem using this combinatorial model. That's what we are going to do in this chapter. Okay, so let's go to the next section then. So first we will find a combinatorial model, a model for orthogonal polynomials using OP means orthogonal polynomials using some tilings that we will call Favard tilings. All right. Okay, so let's define the tilings first. So it's really a simple object actually. A Favard tiling of size n. A Favard tiling of size n is a tiling of a 1 by n board, one square board, say, We have a square board of size 1 by n. So it's like just one row. N squares are there. With 3 types of tiles. There are 3 types of tiles that you can use. So first, red monomino. Red monomino. Monomino means just square. Monomino means just a square. And blue monomino. Sorry, just black. Let's use black. So it's just like this. That's one square. And 3 black domino. The domino is like this, 2 by 1, like that. So we have 2 types of monominos, but there's only 1 type of domino. Okay, so in total we have 3 possibilities. We have 3 types of tiles, and that's it basically. And ft sub n is the set of all Faber tilings of size n. All right, and we have to define the weight. So for each and for Faber tiling, T in ft Faber tiling, define the weight of T to be product. Okay, let's put it this way. Tiling is a set of tiles, so it's a product for all tiles, say T, weight of T. So we have to define the tile, the weight of each tile. Okay, so where weight of black, say red monomino. Let me just use a diagram. Yeah, we can just use this. This is always x. Red is always x. And what about the black monomino? But this, okay. Yeah, I think I have to 1 by n board looks like this. I'm gonna label the squares in this way, like this, starting from 0. So 0, 1, 2, n minus 1. I'm gonna label the squares in our 1 by n board in this way, starting from 0 up to n minus 1. So if this has ni like that, then it's going to be minus bi. Here for red it doesn't matter. The label doesn't matter. And the weight of a domino, so it has 2 integers in it, 2 consecutive integers. Let's say they are I minus 1 and I. So I is the biggest one. In this case, we give the weight to be minus lambda I. So that's basically it. So this is how we define the weight of a Faber tiling. So let me give you an example. N equals 8. So 1, 2, 3, 4, 5, 6, 7, 8. Right, it ends here. So label 0, 1, 2, 3, 4, 5, 6, 7, okay? And let me just consider this tiling. So domino and domino, black monomino like this, and then red like this. Okay, so this is one possible. So T, this is an element in FT8, right? So what is the weight? So this is a domino. So largest one element, largest label is 1. So this will be minus lambda 1. And this is red, so it's x. So every red we have x. For this, it has minus b3, minus b4, minus b7. So if we say this is t, then what is the weight? Product of all of this. So we have 3 x's, so it's like that. b3, b4, b7, and lambda 1. And what is the sign? We have 1, 2, 3, 4, minus this, the sign is plus. So this is how we define the weight of a Favart tiling. Is this okay? And as you can imagine, we can write down the theorem immediately. So, okay, actually, we don't even have to consider orthogonal polynomials. As long as we have this, that's enough. Yeah, even if lambda equals 0. Suppose satisfies. Suppose that we have a sequence of polynomials satisfying this 3-term recurrence. Then Pn has this combinatorial model. We sum over all Favart tilings of n of size n. We take the weight. We sum them all like that. Proof. Easy. Easy by induction, you know. Do you feel this easy? Easy by induction. Because this and this have exactly the same recurrence. Can you imagine? So this recurrence is this. But if you want some more explanation, why is that? You want to find the Favart tiling of size n, and just consider the last tile. We have 3 possibilities, right? We can either, okay, let me just give you just idea. That's the idea. So we have 3 possibilities. If you consider the diagram, so this is 0, 1, n minus 1, n minus 2, like that. There are 3 possibilities. So case 1, I think it's case 1, I don't know, black monomino like that, or black domino like that, or red monomino like that. So once you did that, what happens is this gives you the weight minus b n minus 1, and the remaining part is this. So by induction, we can assume that this is n minus 1 x, right? And also here is minus lambda n minus 1, and by induction, this is p n minus 2x, and this is x. So by induction, this is p n minus 1x. So this means, I think we can just ignore this. So that means, yeah, let's put it this way. That means this is exactly like, we can combine these two together, x minus b n minus 1, p n minus 1, minus lambda n minus 1, p n minus 2. But this is exactly p n x using the recurrence. That means this is also equal to this. So yeah, that's it's simple like that. So finding a combinatorial model for a polynomial, orthogonal polynomials is quite simple. Just if you use the recurrent, 3-term recurrence, you can just get it. Yeah. Okay, so It's not that hard, but the interesting thing happens when we consider the moment. All right, so how can we do that? Let me move on. But before I'll just tell you the exact combinatorial model, let me tell you how one can come up with such a combinatorial model before knowing anything else. So I think this is interesting, and it can be a very useful method when we do some research. Because when we do research, you don't know by definition about that. So you want to find something. You want to find something in your own, right? Instead of just listen to what other people did. Okay. So our goal is to find the combinatorial model for moments, mu n. And first of all, just a note, mu n is important, right? Because it has all the information about the linear function. So it is because they determine the linear function. So it's actually a one-to-one correspondence between moment. If you know moments, you know the linear functional, and vice versa. So understanding the moments will be an important task for us. And suppose we have orthogonal polynomials. Is OPS for some L. Okay, and how can we find the moment? Then, if you apply Pn, if you apply L to Pn, then what happens? It is either 0 or 1. If n is greater than or equal to 1, if n is 0. Why? Because this is really this. P0 is 1. So this is 0 if n is different from n. N is different from 0, so it's true. But why is this 1? Because if n equals 1, this is P0, so it's L of 1, but we assume that L of 1 is 1. So that's why it's 1, okay? This is the reason. This is, yeah, I'm just writing the same thing, but yeah. So let's compute the first few polynomials. P0x is 1, right? And let me copy this recurrence. We're gonna use this very often. We will always so let's compute the first few polynomials. So P0 is 1, and P1, you put n equals 0, then P1 equals, this disappears, so we have x minus B0, right? And P2, you put n equals 1 here, so it's x minus B1, P1, minus lambda 1, P0. So it is x minus B1, P1 x minus B0, lambda 1. So you can compute in this way as many polynomials as you want. So let's just compute this up to this. It's going to be x squared minus B0, B1 x plus B0, B1 minus lambda 1, okay? And let's consider this. So this, we don't have to do that. L of P1 x. This must be 0, right? But what is this? This is x minus b0. So that means it's mu1 minus b0. All right? So we just computed that mu1 must be b0. So actually in this way, we can compute each mu n. So 0 equals L of P2. But we just computed this over here. Because of this, it is going to be mu2 minus b0 plus b1 mu1 plus b0 b1 minus lambda 1. But we already know what mu1 is. Mu1 is b0. So if you plug in mu1 equal b0 and then you can solve this for mu2, you get this equals mu b0 b1 b0 minus b0 b1 plus lambda 1. So if you compute this, it will be b0 squared plus lambda 1. You know how to proceed. So if you compute this over and over, then you will see that mu3 will be b0 cubed 2b0 lambda 1 b1 lambda 1. If you have enough time, you will be able to compute this all just by hand. But if you use computer, it will be faster, of course. And then you can compute over and over. But even at this point, you may have some question in your mind. There is something interesting happens here, right? What is the interesting thing? They're all positive. All the terms have positive sign, right? All have positive integer sign. So it's not clear from this computation that we always end up with positive terms like this. Why can't we have like b0, lambda 1, things like that? But it looks like they all have nice positive numbers as coefficients. So if you do some computation like this, you will be convinced that there is some nice structure in this moment. But how can you guess such a combinatorial model, if there is any? Yeah, because they look just random. The random, you cannot really see nice patterns here, right now, at least. But there is a nice trick to do this. Imagine that we are lucky that we have some nice generating function for this as a combinatorial model. And usually, like we saw before, it will be some set here, before we had like a Faber tiling and weight of t. And just imagine that the weight is all very nice, that they're all monomials in these numbers, like b0, b1, b2 squared, things like that. If this happens, then that means, so what I'm saying is, if there is a nice combinatorial model, which we can guess, for mu n, we can hope that mu n can be written in this way. I don't know, pi in some combinatorial model an weight of pi, where weight of pi is a monomial in these pi's and lambda i's. That'll be the best scenario, right? But of course, it may not be the case, but you can just hope. You can hope for anything. Yeah? If it's not true, you can move on to the next idea. But just imagine that this is really the case. Then how can you guess this? if this is always a monomial, that means if you plug in everything to 1, you get just the number an, the cardinality of an, if that's the case, right? So let's just put all the, so let's put bi's, lambda i's all equal to 1. Then, of course, mu n will be the cardinality of an because it's a monomial, right? So, but we know these quantities, so we can compute that. So in this case, in the case pi's, lambda i's all equal to 1, then you can compute mu1, mu0 is 1, mu1, what is mu1? It's 1, right? This is 1, this is 2, and this is 4. So 1, 2, 4, is that right? Mu 4, and what is this? So 6, 9, like that. And you can just do computation more and more, and you will see a sequence like this: 1, 1, 2, 4, 9, 21, 5, 127, 323, etc. Now, of course, you cannot do this all by hand, but if you can program things, then you can compute this very easily just by computer. Now, at this stage, there is a trick that you can use. There is a web page called OEIS, so https://oeis.com, and then you just go there and then enter this number, and let's see what happens. We can do this together. If I'm connected to the internet, hopefully yes. Oh yeah, I'm already here in OEIS. So if you go to OEIS, then sequence looks like this. So let's type in all the numbers here. So 1, 1, oh, 1, 2, 4, 9, 21, 51. I think this should be enough. Now let's see. And what this web page does is it has like tons of sequences, integer sequences in the database. They find the sequences match exactly this. So let's go. And it says there are 8 sequences matching this. So if you are not convinced, you can type in more numbers. But I think this should be enough. But let's see. If you put more numbers, oh, still 6. But actually, the first one is what we need. But you can see here, it says Matchkin numbers. This means this is a number of Matchkin path, basically, which we already know, right? That means you can guess. This is only a guess so far. We can guess mu n if pn, pi, lambda I all equal to 1. This is going to be the number of Matchkin path of 0, 0 to n, 0. And now that we have a guess like this, we can look at the numbers here again, and then just compare with Matchkin path. So mu1, okay, let's see. Let me copy this. Because now we have a guess, we can work out more. Let me just use this, delete this. So now we want to find the real combinatorial model. So let's generate all Motzkin path. So we know our guess is this should be some generating function for Motzkin path, right? So but here we have only one, like that. Motzkin path looks like this. Here we have this or this. And here it goes like, maybe I can have more space. Motzkin path of length 3 looks like this. I think that's all. And here we have more, but yeah, let's see what happens. We want this have weight B0. So that means maybe if we put the weight of this horizontal step B0, then it works. Okay? And if this is B0, then yeah, we want to put B0, B0, then this gives us this term. So for this, if we give lambda 1, then that will be it. Okay? But how can you put lambda 1 to 2 steps here? I don't know. Let's just say that lambda 1 is here. Okay? Or it is a pair. And then let's proceed. B0, 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 B0. And for this, we have lambda 1. This lambda 1, B0. And now you see this cancels. These two cancels. So this must match with this. And this, it looks like B has to give some weight for horizontal steps. And this must be B1. And this must be a lambda 1. So maybe now we have some conjecture. Or maybe if you have a horizontal step of height I, then maybe the weight must be Bi. And if you have up step, down step like that, then it's going to be lambda 1. But if you compute more and more, you will have a better conjecture, or you will be convinced with your conjecture. And in fact, this is true. And that's the theorem. So in fact, the theorem is, so let me define the weight of a Motzkin path. Let pi be a Motzkin path. Any Motzkin path in general, so it can start anywhere and anywhere, as long as it's weakly above the x-axis. Then we define the weight to be, of course, the product of all weight of the steps. S is a step of pi. This must be S. Where we have up steps, horizontal steps, and down steps. Let's say they all have height like this. I, like that. And actually, the weight of an up step is always 1. We put always 1, and this will be Bi, and this will be lambda I, like that. If we define weight of Motzkin path like this, then everything will work. So let me give an example. Maybe start from here, up, horizontal, down, 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 up, horizontal, down, like that. Then what is the weight? This is 0, level 0, 1, 2, 3. So weight, just ignore the up step. So it's B3, lambda 3, lambda 2, lambda 1, B1, lambda 1. So the weight of the lattice Motzkin path is P1, B3, lambda 1 squared, lambda 2, lambda 3, like that. Okay? And the theorem is, this is a nice theorem due to Vienno. Mu n is really the generating function for all Motzkin path from 0 to n, 0, 0 to n, 0, weight of pi. So it's like this. This is true in general, so you can just continue. The pattern continues, which is very interesting. Yeah. So yeah, what I wanted to tell you here. I didn't prove this, by the way. We will prove this later. My point here is this is what combinatorialists or in general mathematicians do when they do research. So if you just study mathematics from books, then you are just told that this is true, so you can just do this, then this will work. But if you do research, if you have ever done research, then you don't really know where to go. So you really have to find your own way to discover new things. But it's really just a trial and errors. You try this, and then most of the time it fails. So you have to do another method and things like that. But sometimes, like if you try like 100 times, and at least maybe sometimes if you are lucky at once you get nice pattern like this, and then that's when you get excited, and then you can prove things, and yeah. So this is the real mathematics, I would say, instead of just doing reading, and which is also necessary. But if you your PhD student, if you want to pursue your career as mathematician, you will see things like this. Okay. All right. Yeah, actually, instead of proving this, we will prove something more general. So let me state the theorem or definition first. Okay, now let's say that P and X is OPS for a linear functional L. Then for NRS, non-negative integers, we define moments, but we will also define what we call mixed moments. There are two things. NRS, sometimes we will write NRS, or sometimes we will consider NK of this OPS by the following formula. Mu NRS means linear functional applied to x to the n, PRS x PS. And then we divide this by L of PSX squared. And mu and k is a special case of the above one, N0k, which is L of x to the n, pkx divided by L of pkx squared, like that. Okay. So they generalize moments. So what is the moment? What is mu n? This is mu n0, 0, or mu n0. They're all the same. So because what is 0, 0? This 0, so it's 1. This is 0, 1, so this is 1. But L of 1 is 1, so it's just a moment. So it generalizes the moment. And in fact, if you also do the same thing, you can compute this. You can compute this using, you can write them down using b's and lambdas, and you will also find a nice positive patterns. And then you can find a conjecture from there. And actually, if you do enough work, you will be able to find a theorem like this, or conjecture. So mu and NRS has also a very nice combinatorial interpretation. You consider all Matchkin path from 0, R to n, S weight of pi. So this means you start from somewhere above, like height R, you end at height S. And the length is n. So you go things like that. So if you can prove this, then the previous theorem is a consequence, because put the 0, 0 means you start here, you end here. That's exactly the usual Matchkin path. So that will prove the this side, identity. Okay? So this is something that we can prove. Yeah. And actually, I will stop here, and next time we will see two proofs of this. First, using just a recursive method, and the second, using sign reversing involution. And we will, at the end of the lecture, we will see that this is the case, which is really beautiful result in this orthogonal polynomial theory. Okay, then I'll stop here. Thank you for your attention.